Welcome back, Honors Algebra 2 and Algebra 2 students. We are actually on the last page of our investigation packet, which is called Limits. And so I'm just going to kind of briefly talk you through how to figure out limits of a function. And so one of the first things we want to make sure that we do is, like, I have a couple different examples here, is we want to go ahead and sketch a graph of all of these. So what we're going to start with in each of these is I'm going to go ahead and find kind of like the basic information for each one. So the zeros, which remember that just means our x steps, so set the numerator equal to 0, which if I did that I would get 0, 0. My vertical asymptote, I'm going to go ahead and factor this. And then if I set the denominator equal to 0, I would get a vertical asymptote at -5 and x equals +1. And then your horizontal or other asymptote. So if we use those rules that we talked about in the summary, if the numerator degree is less than the denominator degree, then our horizontal asymptote is y equals 0. So if the numerator degree is less than the denominator degree, we have a horizontal asymptote of 0. All right, so let's go ahead and sketch the graph. And I'm just doing a real basic sketch here. So if I have -5 and +1, roughly, and y equals 0, and I have an x-intercept of 0, 0. So you can use your graphing calculator on this to go ahead and sketch the graph if you want. But again, part of the things I know is that, with that, because of that horizontal asymptote, remember when you have kind of 3 sections of your graph, one of the sections will always kind of, well, not always, but a lot of times will pass through that horizontal asymptote, which does seem a little odd because normally with an asymptote, we don't have the graph approaches it but never touches it. The exception is in rational functions in this scenario where there's kind of 3 parts to your graph. So if you went ahead and sketched your graph on your calculator, or if you just picked points, roughly it's going to look like this. And so what I'm going to do here is just kind of get the graphs done, and then we'll talk about limits. All right, so for the next one, the zeros would be, if I set the numerator equal to 0 for g of x, would be -1, 0. My vertical asymptote would only be one of them at 4. And since the degrees are the same, we do the leading coefficient over leading coefficient. So again, degrees, this was numerator degree is less than the denominator degree, tells me it's a horizontal asymptote. When the degrees are the same, it's another horizontal asymptote, but this time it's leading coefficient over leading coefficient, which in this case is 1. And so I'm going to use all of that to kind of graph my stuff here. So x equals 4 is about here, y equals 1, and then we had -1, 0 as an x-intercept. So what happens is my graph is going to do this. And since the branch is down here in the bottom left, my upper branch is going to be up here. All right, so for the third one, I'm going to go ahead and factor this. So 2x + 1 and x - 4. So that way, I'm going to go ahead and factor that numerator so I can figure out my zeros, which in this case would be -1/2, 0, and +4, 0 for my x-intercepts. My vertical asymptote would be at x equals -3. And notice that the degree of the numerator is bigger than the degree of the denominator. This is where you're going to have to use polynomial division. And you are going to have a slant or asymptote. So because this degree is 2 and this degree is 1, the difference between 2 and 1 is 1. So that means my other asymptote, my end behavior asymptote, is actually going to be linear or a slant. So let's go ahead and do the math here. So I have 2x squared minus 7x minus 4. If I say x times what gives me 2x squared, I would say that's 2x. So remember, the rule is you multiply everything by 2x. So I would get 2x squared plus 6x. And then I always kind of tell you guys to add the opposite. So we change all of our signs. So I get -13x minus 4. And then I repeat the process again. So x goes into -13x minus 13 times. And since this is going to give me, I've kind of run out here, right? The next value I could find here is a remainder, which we don't really care about. I'm not going to kind of finish that. So I know my other asymptote, that linear asymptote, is y equals 2x minus 13. I'm gonna kind of do this just because my graph is going to be a little bit different this time. So I have x equals -3, so roughly here, and x or y equals 2x minus 13. So it's a positive slope, but it passes through -13. So I'm just going to kind of sketch it. It's going to look something like this. And then there was a couple x-intercepts, right? So we had -0.5, so maybe about right here, and +4, so maybe about right here. So what that tells me is my graph is kind of doing one of these, because it's in that upper corner, which means the other part of my graph has to be down here in this little region. All right, so once you have the graphs done for your functions, what we're going to do is we're going to talk about how to find the limits for each of these. So we have two different kinds of limits. The first one is an end behavior limit. So an end behavior limit is kind of dealing with like your horizontal or other asymptote, your end behavior asymptote. So if you'll notice, the limit is kind of what we were used to when we did this before. So the limit as x approaches -infinity and the limit as x approaches positive infinity. So you're going to have two limits for every one asymptote. So for your end behavior limits, it's always going to be as x approaches -infinity and as x approaches positive infinity. So again, what that really means is what happens to your graph when x gets smaller and smaller and smaller, and what happens to your graph when x gets larger, larger, and larger. So on this one, if we look at our first graph, and that's why I had you guys graphed these. If we look at our first one, f of x, as x gets smaller and smaller and smaller, where does our graph go? Well, so as x gets smaller and smaller and smaller, our function is approaching that horizontal asymptote. And so what happens, f of x approaches 0, because that's that horizontal asymptote. As x gets bigger and bigger and bigger, where does our function go? Well, it's approaching that horizontal asymptote of 0. So what you might notice is on a limit, if you have an end behavior limit, it's always going to approach the horizontal asymptote. So for here, if we use that same kind of concept, our horizontal asymptote is at 1. So we should show that our limits are going to approach 1. So as x gets smaller and smaller and smaller, notice how our function gets closer to 1. And as x gets bigger and bigger and bigger, notice how our function gets closer to 1. So again, this is your horizontal asymptote. So for an end behavior asymptote, or end behavior limit, it approaches your end behavior asymptote. So in this case, it's that horizontal one. When you have a slant or other kind of asymptote, what you'll notice is x gets smaller and smaller and smaller, our function is getting smaller and smaller and smaller. So it's approaching -infinity. And as x gets bigger and bigger and bigger, our function gets bigger and bigger and bigger. So anytime you have an end behavior limit that's approaching infinity or -infinity, what this tells me is that this is a slant or other asymptote. So in other words, it's not horizontal. So why that's important is if I just gave you this information, I didn't give you a graph, you would be able to tell me that this function has an other asymptote, that it's not a horizontal asymptote. Or if I gave you this information, you'd be able to tell me what the horizontal asymptote is. In addition to end behavior limits, we have vertical limits. And so what that basically means is that for every vertical asymptote, we have two limits. So how we read this is like, so imagine you have this line right here. So this was at -5. So notice how I wrote x, the limit as x approaches 1 negative, and the limit as x approaches 1 positive. The limit as x approaches -5 negative, and the limit as x approaches -5 positive. So that's kind of a new terminology here. And so what this means is when you have, like, for example, the limit as x approaches -5 negative, that means what's happening to the function on the left side of this graph. So this little negative here means the left side, whereas this positive here means the right side. So same thing here. This says the limit as x approaches 1 negative. That means what's happening on the right of that asymptote, and then the limit is x, I'm sorry, that's left. What is happening on the left of that asymptote, and then the limit as x approaches 1 positive would be what happens on the right of that asymptote. So let's look up here. So you have your -5. On the left, your function's going down, and on the right, your function's going up. So on the left, it's going to -infinity, and on the right, it's going to positive infinity. And then for 1, on the left, it's going to -infinity. On the right, it's approaching positive infinity. So what's nice about vertical asymptotes is the answers are always going to be either infinity or -infinity. So those are always going to be your choices for what happens. Because obviously, if you have a vertical line, the graph is going to approach it only from two different directions. Either it's going to go up forever or down forever. Let's look at another one. So this is an asymptote at 4. So we're asking what happens on the left side, what happens on the right side. So on the left side, it's pointing down, the right side, it's pointing up. So negative infinity, woo, and positive infinity. Again, it doesn't always have to be in this order. You know, depending on what graphs we could have different looking. This could be positive infinity, and this could be negative infinity. So it really does make it does change. All right, so on this one, when we have a slant asymptote, it really doesn't do much difference because it doesn't affect our vertical asymptote. So again, same deal. What happens on the left of our vertical asymptote, what happens on the right? So on the left, it's pointing down, and on the right, it's pointing up. So again, just to kind of recap with vertical limits, you're looking at your vertical asymptote, and you're looking to see what happens on the left versus the right. All right, let's jump ahead, and we are going to look on page 197 of your student journals. So I wanted to jump ahead to this so that we can kind of talk about some other kinds of graphing. So we have focused a lot on graphing rational functions, which has been great. However, there are a couple different formats that I would like you to see. Well, one in particular. So we already know that a rational function is kind of like a ratio of two polynomials, right? So you have p of x over, I don't know, q of x. So it's a polynomial over a polynomial. So quadratic over a linear, a cubic over a linear over a linear. Doesn't really matter. A constant over a cubic. So basically what we're getting at is just the ratio of two polynomials. And so that's why a lot of this stuff is kind of familiar from back to our polynomials unit. So there's a couple different examples of how to graph a function, and then also talk about how this relates to like the shifts, right? Like, so is it shifted left, right, up, down? Is it shifted vertical stretch or horizontal stretch? Something like that. So let me give you an example. So let's say I have g of x equals 6 over x, and then I have f of x is equal to 1 over x. So how would these graphs look different? All right, so one of the things I would maybe have you guys do is graph this. So there's a couple things that we probably already know. Number one, there are no x-intercepts for either of these because if I set the numerator equal to 0, I have a constant term and there is none. And then the second part is they both have a vertical asymptote at 0. So I'm going to go ahead and put that in. And they have a horizontal asymptote at 0 since the numerator degree is 0 and the denominator degree is 1. The numerator degree is less than the denominator degree, which causes my function to have a horizontal asymptote at 0. So if you graph this, so I'm just going to go to my y equals here and type in 6 divided by x. And then I'm going to go ahead and graph 1 divided by x. Like, what does that 6 do to our function, right? So that's what we're kind of trying to figure out. So here's 6 divided by x, and then 1 divided by x. So notice that the 1 divided by x is closer to the origin. So it's closer to the x-axis and the y-axis. And so that's what this 6 does. Imagine that this 6 is like you're multiplying. So think about factoring out that 6. If I factored out the 6, it would be 6 times 1 over x. So what that's really doing is that's your vertical stretch. And so, for example, it's stretching it more up and down. So it's pulling it. So it's pulling it away from your x-axis and away from your y-axis. So this is the g of x equation. Whereas if I had the 1 over x, it has less of a stretch, so it's going to be closer to your x-axis and y-axis. So again, I want you to think of that as your vertical stretch, just like we've done in other functions, that if you think of it in terms of like 6 times 1 over x, remember that's your vertical stretch. Another example, let's go, you're going to see functions kind of written like this. So g of x equals -2 over x minus 1, and then they're going to have a k value. So what this is basically kind of like for a rational function, this is as close as we get to like vertex form. There's not really a vertex in these types of functions, if you hadn't already guessed, just because of the way they look, right? But in these, what we're looking at, let's go ahead and do a kind of a quick sketch. I'm going to have an x-intercept of 0. So what happens here actually is it's a little bit different in terms of graphing it. So we still have a vertical asymptote at 1. But because of this k value, this is your horizontal asymptote. So kind of like in a trig function, the k value was your midline. In a log function, your k value was, or actually an exponential function, your k value was your asymptote, right? So same deal here. Your horizontal asymptote is going to be at 3. So that's kind of the quick way of trying to figure out what my horizontal and vertical asymptotes are going to be. And then if I sketch a graph, this one has no x-intercepts, which means that my branches, if you graph this in your calculator at least, you would notice that the branches are here and here. And again, you can plug in points, or you can, sketch it kind of, like I said, with your calculator. All right, so to kind of recap, and this is does go over some nice steps here. So step 1, draw the asymptotes x equals h and y equals k. So notice that they're putting h and k. So this is kind of your vertex form of your equation. So that's your first step, and that was what I was telling you here, is this is your vertical asymptote, and then this is your horizontal asymptote. That's all they're really kind of doing. Plot points to the left and right of your vertical asymptote, so this is where you kind of get the feel for what the shape of that curve is going to be, and then draw the 2 branches of your hyperbola. They call it a hyperbola, so it's of the rational function. All right, so let's kind of look at this extra practice, and we're going to chat a little bit about some of these examples. So what they're asking you to do here is graph the function, then compare the graph with the function 1 over x. So let's go ahead and sketch kind of an x and y axis here. So this is very similar to the one we just did, right? So we have a vertical asymptote of 0, we have a horizontal asymptote of 0, and then all we really need to know here is kind of where is this located? Well, there are no x-intercepts in this graph. If I graphed it, I would have so again, if you think of it as 0.25 times 1 over x, this is your vertical stretch. So this is actually not a vertical stretch, but more so a vertical shrink, because this is like 1/4, right? So it's up 1 over 4. So what this is going to do, we'll use blue for g of x, it's going to cause my function to be closer to my x-axis and my y-axis. Whereas if I graphed 1 over x, we'll use green for this one, it's going to have kind of a similar idea, but it's going to be further away. So if it's a vertical shrink, in this case, the 1/4, that number out in front is going to cause my graph to be closer to the x-axis. So remember in the example I gave you on here, over here I should say, the 6 was your vertical stretch because it was a whole number, whereas 1/4 would be a vertical shrink. So if it's a vertical stretch, it's further away from your origin, further away from your both axes, and if it's a vertical shrink, it's closer. So what happens here is, if you might notice, we have, not only do we have a negative, but we also have the 2. So what's going to cause this is going to cause a reflection in our axes. So let me show you what that would do. So I haven't talked a whole lot about reflections, but that 2 is going to cause our function to be further away from our axis. So it's almost like you're going to be thinking of this, so if I'm going to graph this in blue, like further away from your origin, from your x-axis. So when we have our asymptotes, I'm going to throw those in there. All right, so on this one, because of the negative, instead of being in quadrants 1 and 3, we're going to be in quadrants 2 and 4. So it's going to be something like this, and then something like this. They're still approaching my asymptotes, they're just further away from my origin. And then for the green one, so go back to y equals x. Again, this one, because 1 over x is not reflected, it's going to still be in quadrants 1 and 3. So because that wasn't reflected, we're going to go ahead and leave it in that. So that's going to look a lot different, right? All right, let's do a couple others on the next page, and then I'll give you guys a chance to try some on your own. So we're on page 199. All right, so we have this kind of format of your rational function. So we hadn't done these until now, so this is definitely a little bit different. So remember, if you're graphing this, what you're looking at is So I'm going to go ahead and draw in my axes. So what you're looking at is your vertical asymptote would be 3. My horizontal asymptote would be 5. 1, 2, 3, 4, 5. Kind of off my grid here, and that's okay. So that's going to be where, so again, the vertical and horizontal asymptotes are actually easier to find when it's in this format. Just the problem is that most rational functions aren't generally in this format, but I wanted to show you kind of some that were and some that weren't. All right, so we have no x-intercepts, and so my graph is never going to touch 0, 0, or it's actually never going to touch my, my x-axis. Let me rephrase that, hold on. No, because if I plug in 0 for y, I would get, yeah, I'm going to have 1. So what we're going to want to do here is we're going to go ahead and we can do a quick sketch on our calculators. Let me clear this stuff out of here. So if I did 1 divided by, and I'm going to put this in parentheses, x minus 3, and then I'm going to go plus 5. Let's see what I get when I graph that. So be careful on this one because we're so used to looking at the numerator and saying this is my, is there an x-intercept? Because of this 5 out here, we can't just use that, set the numerator equal to 0 to get your x-intercepts thing anymore. And so you do have to be careful. You can either plug 0 in for y and solve for x, like I said, or you can sketch it. So what we know here is that our function is going to be in quadrants. Well, it's going to be kind of over here and over here, our 2 branches. And then it asks us to state the domain and range. So I'm going to do domain. We're going to use set notation. So all real numbers except for your vertical asymptote. So x does not equal 3. And then my range would be all real numbers. And then on this one, it would be all except for that horizontal asymptote. So y doesn't equal 5. And that would be my domain and range. I'm going to leave number 4 for you guys to try, and that way you can ask questions about that if you kind of do that one on your own. All right, in numbers 5 and 6 here, what we're doing is you're graphing this, but you're also then going to tell me kind of the shifts that apply. So I'm going to do number 5, and I'll save number 6 for you guys to try. All right, so let's go ahead and draw in my axes here. Okay. So this one is actually not in the format. So it says to rewrite the function in this format. I am not going to require you to do that because we're comfortable working with rational functions that are in this format. Now, you are welcome to do that if that helps you. I don't think it's as beneficial. So what I mean by that is I'm going to go ahead and graph this like I did in the investigation. So I have I have a vertical asymptote at 5. So here's my vertical asymptote. I have an x-intercept at -2. So I know I have a graph or a point over here. And I have a horizontal asymptote at 1. And the reason why is because my degrees are the same. And since the leading coefficient divided by the leading coefficient gives me 1, that's my horizontal asymptote. All right, so this one was actually kind of easy in terms of how the graph is going to look because we know of this x-intercept. It's going to kind of do this. This is why I like kind of graphing in this format. So we know we're going to have our branches in quadrants, kind of like quadrants 1 and 3 again. It asks us to describe the graph of G as a graph of A over X. So what this does is, like, how does this relate back to like A over X? In other words, like a number over X. So one of the ways that you could do this is you could think about what the function 1 over X would look like, or A over X, which would just be at the origin. So like it would start here, right? So that was kind of like our normal functions that we did. I don't say normal, but our other functions that we did, like this one, like 1 over X, had a vertical asymptote at 0, a horizontal asymptote of 0. So what did we do? So think about, like, we kind of like moved this origin to here. So see how our horizontal and vertical asymptotes now cross here? What did we do to get from here to there? Well, we moved it right 5 and up 1, I should say. So my shifting is right 5 and up 1. And so really what you're looking at is from the origin, so from our original X and Y axis, how did I get to this new kind of X and Y axis of sorts? And it's our vertical and horizontal asymptotes. And then just look at how you shifted your function. I will show you how to write this in this format just in case you want to know. Okay, so let's go over one example of how to do that. So how you do this is you actually use polynomial division. So I'm going to divide. So I'm going to do x minus 5 and have it's being x plus 2 is being divided by x minus 5. So x times what goes into x, and I get 1. So I get x minus 5. So this is, let's change our signs, I get 7. So what happens here is once you do your polynomial division, this becomes your a value. So this becomes your a value. So like your remainder is your a value, and this becomes your k value. So we already have this as kind of our denominator here. So remember our generic form is a over x minus h plus k. So now I would rewrite this as g of x equals a, which we said is 7 because that's your remainder. The x minus 5 kind of stays put because that just is going to still be your denominator. And then plus 1. So that's your new function if you wanted to write it in this format. So again, you would notice that it has a horizontal asymptote at 1, a vertical asymptote at 5, and then if you did the x-intercept, you would find that it has an x-intercept at -2. I would try these two, and then, if you have questions, I would bring them to class, and then obviously there's some additional practice on big ideas. What I can do right now is, give you guys a chance to try them, and then if you have questions, you can ask in class and we can go over those. All right, that's it for now. Bye, everyone.